Hey everybody, it's Ripley. I am back again. We're going to talk about hypothesis testing with two samples now. Now, think about what we did in the last chapter. What we had is we had a population, okay? And what we did is we guessed something about that population. So we had a null and an alternative hypothesis, and we either guessed something about the mean or about the population proportion, right? And we said that the mean equaled something, or that the mean didn't equal something, or that it was less than or equal to something, or something of that nature, okay? And then what we did is we pulled a sample out of that. So we pulled a sample out of that, and we found an X bar, and we either knew the standard deviation of the population, or we had to use the standard deviation of the sample. Remember, that was the difference between being able to use a Z-test and being forced to use an S-test. If we were testing around P, remember, they had to be independent. It was more of a binomial situation. The requirements were in P and NQ were both greater than or equal to 5, et cetera, right? And then we did our test. We had a test of some sort, and then we either used confidence intervals, we used critical values, and we used p-values to determine whether or not, remember, wait, I've got a little ahead of myself. Remember, we always established an alpha. We also had an N, right? There was always an N here. And then we used all sorts of techniques to figure out whether or not it was feasible to reject the null hypothesis. Okay? Now, when we're testing two samples, what we're saying is, let me give you an example, okay? The easiest way to explain this is, I believe that the proportion of women that support a specific candidate is greater than the proportion of men that support a different candidate. Okay, so here's the way this works. Let me show you. We've got women over here. We have a population of women, and we have the population of men. Like before, like with confidence intervals and hypothesis testing, we're going to start with proportions. Okay? Now, we've got all women, all voting women, and all voting men. And then we do exactly the same thing. We grab a sample of them, and we bring that sample out. We grab a sample of men, and we bring that sample out. Okay? And then we're going to figure out a p-hat for these guys, which we're going to call p-hat 1, and we're going to figure out a p-hat 2 for these guys. And we're going to have n's and p-hats and all sorts of stuff that we're going to deal with. And then we compare these two. And we decide whether or not there is truly a difference. Now, think about what, let me cut this off a little bit. Think about what the null and the alternative hypothesis for this would look like. Because really, if you think about it, if I know what the null and the alternative hypothesis look like, and I've chosen my alpha value, then all that I need is the test value. All right? And I'm not going to insult your intelligence by going through a whole bunch of these. What I'm going to do is I'm going to give you the test value. I'm going to give you an example straight out of the book, because by now, in other words, I'm going to give you what the test is. In other words, you know, whether it's a Z, a T, whatever. I'm going to give you, I'll write up what the assumptions are. Well, and then I'm going to give you guys an opportunity to try it on your own, and then I'll do it out for you, okay? So think about this. The null and the alternative hypothesis, just like before, the null hypothesis is, that the proportion of women is equal to the proportion of men. It always contains the equality, always, okay? And then this can either be P1 is not equal to P2, P1 is greater than P2, P1 is less than P2, etc. Just like we did before, okay? Now, there's a difference with this. We don't traditionally do this with proportions, but I do want to set up. Let me say, I believe, I'm going to make a claim. I believe, that the difference in support of, wow, that's terrible handwriting. I'm sorry, you guys. Of candidate A of women You guys, the construction's going crazy today, so bear with any weird noises, okay? Candidate, what's going on here? A of women over men is 5%. In other words, it's 5% higher in women than it is in men. I suppose I could have written that a little bit better. Now, the difference between when we're doing this with just one sample versus two samples, you have to realize that what we're doing here is we're talking about two samples. The difference between when we're talking about one sample and two samples is that we can actually talk about differences. So I could actually write the null hypothesis up for this as P1 minus P2, the true proportion of women. 5% is going to, let's make that 8%, because otherwise we might get a little confused with alpha. Let's say that it's 8%. Okay, that P1 minus P2 equals 0.08. All right, versus the alternative hypothesis, which is P1 minus P2 is not equal to 0.08, is greater than 0.08, is less than 0.08, etc., etc., etc. Now this is pretty cool because it allows us to do this little funky business right here, which is really nice. In other words, we don't just have to say that they are equal to each other. Because really, if you think about it, let me change colored pens right here. This is exactly the same as saying P1 minus P2 equals 0. We can be much more specific in what we believe the difference to be, and then we can test that difference. All right? Now remember, this only works when we're talking about two samples. Not just one sample, because then we pull a sample out and we say, okay, the mean or the proportion or something equals a value. But now we're talking about the differences between those two samples. All right? Okay, cool. Now, before we get crazy, like I said, these are really simple. We're going to blow through these quickly. The only difference, excuse me, between what we're going to do here and what we did in Chapter 8 is the test, the T, the Z, etc., is a little more complicated, but we're not going to panic, all right? The first thing that we need to do is we need to talk about the assumptions, okay? First things first, the assumptions. So right now we're talking about differences. That looks terrible. Whoa, wow, differences, pardon me, excuse me, in proportion. Let's do this one first, just like we did before. Start with proportion, work our way to means, okay? Assumptions. All right, number one. The number one assumption is that the samples are independent. Samples are independent from each other. Now think about that. What that means is the probability of a certain person favoring a candidate, a woman favoring a candidate is different, is unaffected by the probability that the man favors a certain candidate. Now, think about that in the context of the problem that I just talked about. You couldn't, in other words, you couldn't sample a husband and a wife. Theoretically, there'd have to be a strong argument that said, okay, he does not affect my voting and she does not affect my voting, because those wouldn't be independent, would they? I mean, think about that. If you affect one another's voting, it's like, honey, I think you should vote for candidate C, not candidate A. Well, guess what? You potentially you violate this independence assumption, okay? And then standard issue, it's a proportion. So from each population, in my case it was the men and the women, all right, from each population, we draw a sample, all right, we'll call it of size n, such that NP1 and NP2 are both greater than or equal to 5. Just like before. All right? Just like before. Nothing to it. Okay, now, the formulas for this are beefy. You're going to have to bear with me for just a second. Okay? Now, again, just kind of plant it in your brain, just to keep it simple. Think of P1 as it's the population proportion for population 1. Population 1. In this case, the women. Okay, P2 equals population proportion for population 2. In other words, those are the parameters, okay? Those are the parameters. Let's see, N1 is sample size, and this is going to get a little boring, sample size from population 1, okay, and N2 is the sample size from population 2, et cetera, right? X1 equals the number, remember, this basically comes from binomial, all right, of hits, just like before, from from N. Whoa, sorry about that, my eraser's acting goofy. From N1. In other words, I take a sample size of, of 600. I say, do you favor candidate A? X1 would be the number of women that said, yes, I favor candidate A. Okay, so let's see, X2 equals number of hits from N2. Easy peasy. So I know that P1 hat equals sample proportion for pop1, and P2 hat equals sample proportion for P2, or for population 2 portion. Sorry, you guys, that's terrible. I apologize. Okay, so nothing to it. I also know that, let's see, might as well be exhaustive here. I know that 1 minus P1 hat is equal to Q1 hat, and 1 minus P2 hat equals Q2 hat, etc. Now, there's something in here called a pool. We're going to need this. This is called a pooled sample. I'm going to change colors. You know what? Just because this is new and different, and I don't want to be glib about announcing this, because we're going to use it in our formula. We're going to use it in our test statistic, okay? All right, here we go. So we're going to do, let's do red. We're going to do pooled sample proportion. Now, again, why we use this, why this is what it is it's above the scope, it's beyond the scope of this class. This is an introduction to statistics. I want you to see it. We're going to do a lot of these by hand. These get a little trickier to do in absence of, to do some real compelling work in absence of computers, but computer software does all of this for you, and it actually spits out, it's got this output that it spits out. But I want you to do these by hand because I want you to see why. And we're not going to do many of them. I mean, we're really only spending a day in this chapter, so it shouldn't be too much torture for you. Think of this as, this is all that we're doing is we're pooling x1 plus x2, and we're dividing it by n1 plus n2. And I'll show you why we need this in just a second. So we know that Q, the pooled sample Q really is just equal to 1 minus this P bar, okay? Think of it almost, I mean, if you look at it, what it is it's the mean of the proportions, right? It's the mean, it's the overall mean proportion. So you take the sum total of all of the, yes, I support candidate A, and I divide it by the total number. In other words, this thing ignores any differences between the populations, okay? Now, here's where it gets fun. All that you need is a z statistic, okay? We're going to do it with z, remember, because we know with binomials, as long as this guy right here is satisfied, we're in good shape, all right? Let's see. So all that z is it's P1 hat minus P2 hat, okay, minus P1 minus P2. Now remember, samples, parameters, and I'll make you guys use these here in just a sec, so no panicking, okay? And this is divided by the square root of P bar Q bar over N1 plus P bar Q bar over N2, okay? That's all that it is. That's the z, okay? This is if we're going to use, this is the guy that we're going to use if we want to do a p-value or a critical value, right? And then for a CI, you can almost look at it and figure out exactly what it is, all right? You can almost look at it so check it out. I know that the difference in P1 minus P2. Remember the difference in the proportions, excuse me. All that it's going to be is P1 hat minus P2 hat minus the error. Put a little thingy-dingy there. And we're going to have P1 hat minus P2 hat plus the error. Now, what's the error? We could actually go through our algebra here, but I'm not going to force you to do that because you would all revolt on me and I'd end up dead, and I don't want that. And this is just z alpha halves, just like we did before, right? So it's based on our alpha, and then I'm going to have square root of, this is going to be P hat 1 Q hat 1 over N1 plus P hat 2 Q hat 2 over N2. Okay? That's if I want to build a confidence interval. That's it. There's no difference. In other words, let's be careful. There are differences just insofar as where this test statistic comes from. It's more complicated. It's a more complicated numerical process. However, if you think about it, it's still going to work out the same way. Once I get this number, I'm either going to look at the p-value, I'm going to look at the critical value. I could build a confidence interval and figure out if my mean ends up, my proportion ends up in this confidence interval. In other words, the techniques that we use to determine whether or not to reject or accept the null hypothesis, we're still just testing around this guy and this guy. These are just the values that we use, all right? So there are your test statistics. These are what you're going to use. Are you going to have to memorize these? Of course not. In fact, we're going to hang them up with the assumptions in the room so that you'll be able to use them. However, you are going to have to be comfortable using them. So let's go through a process. All right, let me dig a problem out for you guys directly from your textbook, and I'll let you do it and I'll do it, and we'll compare notes afterwards and we'll see how we did. Okay? Okay, let's put it to the test. You ready? On page 458, there is a problem called Are Seatbelts Effective? It's number, what number is it? It's number 16. Okay, Are seatbelts effective? Is it A or E? It's an E, isn't it? I always screw that up. Effective. Okay, now here's what I'd like you to do. I'm going to push, I'm going to stop, and then I'm going to do the whole problem out down here. But I would like you to try it all on your own. All right, it's number 16. It's not number 15. Number 15 is just building a simple confidence interval. Okay, now I'm going to do it all out, and then I want you to check your work. If you can do this one, you're golden. Okay, when I come back, the problem's going to be completely done here. And I'll walk you through it. It won't take very long at all. Okay, so good luck. Hit pause. Try it out on a piece of paper, and I'll meet you back here in just a sec. All right, here we go. Hopefully you ended up with something like this. Are seatbelts more effective in saving lives? All right, they either, well, I think in the problem it says, I forget what it says. It says, is there a higher rate of fatalities in drivers that don't use seatbelts? Excuse me. So basically, are the population proportions between let's try this again, for drivers using seatbelts, which would be these guys, versus drivers that aren't using seatbelts, is the proportion of fatalities higher in those not using seatbelts? Well, we know, I mean, this is a pretty obvious problem, but watch how it plays out. They're either equal, or we know that we're really checking to see if those using or not using seatbelts is higher than those using seatbelts. So all I did is I stumbled through, what I really needed was P1 hat and P2 hat, right? So I just stumbled through. Let's see, X1 was 31 out of 2823. Clearly they're independent, right? So I mean, you can't be wearing a seatbelt and not be wearing a seatbelt. I suppose you could gather it from the same accident, like some guy was wearing a seatbelt and some guy wasn't, but that doesn't really matter. All right, so this guy right here ends up being my sample proportion of people that died who weren't wearing seatbelts. This was a sample proportion of people that died who were wearing seatbelts, and then I found my pooled. I suppose I was a little remiss here. I didn't actually come up with Q bar, or my pooled 1 minus P, right, which would just be 0.99, what is that, 56? Okay, I built my little thing. I chose to use a critical value because I had a sneaking suspicion that it was going to be more difficult to find the p-value because I was guessing that our test score was going to be huge, and as it played out, it was. So all that this is p hat 1 minus p hat 2. We know because of the way in which our null hypothesis is written, I know that p1 minus p2, the true population proportions for both samples, or excuse me, for both populations is 0. I plugged, I chugged, and this is what I got. And then this is my summary. Since z equals 6.19 falls in the critical region, it's larger than 1.645. By the way, that was my critical value, right, for alpha equals 0.05. Excuse me, which, I mean, if you think about this, if we had to figure out the probability of getting values at least as extreme as z equals 6.19 standard deviations away from the mean, the probability of that's going to be very, very small. It's certainly going to be less than 0.05. We reject the null hypothesis. It appears that fatality rates are significantly higher in drivers not using seatbelts. Ta-da! And we're done. And that's it. That's how it works. That's all we got to do. It gets a little trickier when we build confidence intervals, but we'll do that in class. We'll play with that. It's still this. It's just a variation on the theme. Okay, the theme of, are we going to use critical regions? Are we going to use p-values? Or are we going to use confidence intervals? All right, it's just the same. It's just that the calculation gets a little bit nastier. Okay, we're going to go ahead and move on to the next section, and I'll see you in class tomorrow.